Let's do another example of finding a derivative by the difference quotient and then just talking about what it means. So again, we can always start off with our definition when trying to find a derivative. But as I said in class, there are a lot of shortcuts. That's what we're going to be focused on in chapters 1.5, 1.6, 1.7 are what are the shortcuts? How can we do this where we don't have to do a bunch of algebra every time? But basically, f prime of x is always equal to, whoops, I don't know why I wrote x there. It's always the limit as h approaches 0 of f of x plus h minus f of x divided by h. And I always recommend starting off by figuring out what is f of x plus h on the side. Here it would be x plus h quantity cubed. And this one is, again, this would not be x cubed plus h cubed, common error here, because x plus h cubed means x plus h times x plus h times x plus h. That's always what exponents mean. And to properly multiply that out, we will need to FOIL. So I'll go ahead and write that out. And then to FOIL this, there's a shortcut for FOILing when it's the same thing. It would be x squared plus 2 times the inner product plus h squared. And then I'm going to have a third one. There actually is a shortcut for expanding such things by using Pascal's triangle. And I'll go ahead and do the expansion and leave it for you to check me to make sure I'm not messing it up. So the shortcut, again, I'm going to have 3 terms times 2 terms. If I multiply this all out, I would have 6 terms. But a lot of those terms are going to combine, which you'll see if you finish out the FOIL. But at the end of the day, my full product here will be 3x cubed plus 3x squared h plus 3x h squared plus h cubed. And that would be all of the algebra behind x plus h quantity cubed. And so that's, I'll go ahead and insert that into my numerator. So I'm going to have the limit as h approaches 0 of, let me try to write this a little bit better here, but I'm going to have x cubed plus 3x squared h plus 3x h squared plus h cubed. And then I can't forget to subtract f of x. In this case, it's just x cubed, so it's not too terrible. Minus x cubed. And that would all be divided by h. Again, there will be cancellation in general, not always, but with a lot of algebraic functions. And this will leave me with everything left over has h in it. So now I could divide each term by h, because h divided by h will cancel. H squared over h will make h, and h cubed over h will make h squared. So I'll go ahead and divide through by h next. So this would be equal to, oops, I don't want red, equal to the limit as h approaches 0 of 3x squared plus 3xh plus h squared. And remember, since this is a polynomial, I can use direct substitution of the limit upon it because polynomials are always continuous. And essentially plug in h is equal to 0. So that 3x squared, that limit will not affect it because it's constant with respect to h. 3xh, plugging in 0 here will give me 3x times 0, which is of course 0. And plugging in 0 in for h squared would give me 0 as well. So these two terms go to 0, or one of the ways we often draw this is this term goes to 0, this term goes to 0 upon substitution of h is equal to 0 into that limit. And this leaves me with 3x squared. And again, this would be as simple as I can get it, and this would be the answer to my derivative in this problem. So again, we would say that the derivative of f of x is equal to x cubed is equal to 3x squared, or f prime. Again, we refer to this as differentiating the function, finding the derivative, or again, we might refer to this as a slope function. And another, what it asks us to find the derivative and use it to find the slope of the tangent line at various points. This will give us that slope wherever we want. So let's just say we plug in 0 or plug in 1 or whatever we want. Let's plug in 4. All of these will give us the respective slopes at those points along the function. So 3 times 0 squared is 0. Our slope at the origin should be 0, meaning it should have a horizontal tangent line because it has a zero slope, no rise to it. At 1, we'll have 3 times 1 squared, which is 3. So if we go to the right one on our function, we should see that the slope is 3, which is significantly stronger and positive. And if we go to 4, we would have 3 times 4 squared. 4 squared is 16 times 3 is 48, I believe. And we can see that the slope becomes very, very strong as x increases. And if you remember the shape of an x cubed function, as you move to the right, it gets very, very steep, very, very rapidly. It looks something like this. And as we move to the right, the slope gets further and further. And if we go to the left on the curve, the slope is actually still positive. Noting that our derivative function is x squared, this will always be positive as well.